Now really, when it comes to monitoring, sniffing, whatever, exploitation of computer networks, it just kind of comes down to reading the RFCs, which are spec sheets for protocols or file formats, and then just reading the actual file format structure. And for this specific project, which will be network sniffing, that also holds. Now in this video I'm going to show you how to create a simple Pcap parser, and Pcap is a file format that is specifically meant for network traffic captures. Pcap is used all over, like exploitation, analysis, monitoring. So this should be a good simple starter project, because we're going to be making something where we can use the code that we make and then apply it to an even more complex project. So this isn't like one of those projects where you learn the fundamentals, but because the code may not be useful for more advanced projects. That isn't the case here. We could actually use the code we're going to write here for something better. Now, first we actually have to look at the file format that we're going to be working with, which again is Pcap. Now here I have it saved under struct. Okay. Now this is the Pcap file structure. So Pcap consists of two parts. Well, first, a single global header, and that gives you information about the file overall, and then a packet record. And essentially this just means that for each packet that is captured during whatever you use to listen to a network, it'll create an individual packet record. And you can see that the header and the specific okay, so a global header is for the file overall, while a packet record has its own individual header, and then it has whatever traffic or whatever protocol data it captured. This could be TCP, Ethernet, ICMP, any protocol. Now this file format is used by essentially all of the network adjacent tools, such as Wireshark, Tshark, TCP dump, and they use it to read/store network traffic. Now you can notice here that these packets, or these file types, are essentially just kind of like a sequential puzzle, in the sense that, okay, so what is this telling us? Given this file type, the first 8 bytes are always going to be the magic number. The magic number is just kind of like an identifier for the file type. That's kind of how the file command in Linux work. It just reads these magic numbers and tells you, oh, okay, it's a file type. It's a file of this type. So like we have 8 bytes for, or I'm sorry, 3 bytes for the first, or no, these are 4. Whatever. The first few bytes. I'm sorry. The first 4 bytes are for the magic number, and then 2 bytes for the major version and 2 bytes for the minor version, and then we have these reserved, and then snap length and link type. That kind of applies here as well. We have 4 bytes for the timestamp, and then another timestamp, and captured packet length, and the original packet length, that's the packet that's actually being, I'm sorry, the network traffic packet that's actually being stored. Now, this is what kind of makes it really simple. You're just, okay, so if the specification tells you read 8 bytes for this piece of data in the file, then just do that. And then when you read those 8 bytes, because of the way I/O works in C, if we consider this like the cursor of when we're reading this file, after we read the magic number, now we're at the major version. We want to now read the major version, we just read it 2 bytes. Same here, after reading those 2 bytes, we're now at the minor version. If we want to read the minor version, we just read another 2 bytes. Now, this is really helpful. This is kind of a simple way to do it. Another potential way of doing it is to use the structures that are specific for Pcap, and we'll show those in the code. Essentially, rather than having to read one by one, what we can do is just declare a structure, and then because the structure mimics the actual file structure, like it's a C struct, but it has all these fields, it does separate, like the fields in the C struct are at the same offsets from the start. So rather than like having to read these 3 to reach this, we can just directly access this. And that's kind of a cool thing about C structs. Now, the big thing here is that when you're writing a parser, specifically for Pcap, again, the packet data itself, it can be TCP, UDP, Ethernet, whatever, ARP, and you should know at this point that those packet types have different amounts of data. They store different things. Because of this, when you're writing a parser, you do have to account for every type that you want to account for. This could be easily done with a switch statement, but in this case, we're really just going to be focusing on Ethernet, IP, for the IP layer, and TCP. We're not really going to focus on like ARP or UDP or anything like that. But in a real parser, you would want to use a switch statement. Now we have an idea how that file is structured. We can actually look at one with sample.pcap. Now, obviously, this just kind of looks like junk data, and I guess to us it is junk. But if we scroll up, we should see what we saw in the struct.txt file. We see that 4 bytes are being used for the magic number. They don't really mean anything, but if you were to open, say, a ELF file, like just to give you a quick example. An ELF file, which is just an executable, it has the actual signature of ELF. That's kind of the same concept here, except I guess this doesn't really resolve to anything. And then we did see that the major number is made up of 2 bytes, and we can see that the major number is 2 here. The minor number is 4 for this packet. And then I guess we would have these reserved bytes, and then we get into the actual data. So that's just kind of to visualize what we're going to be working with. Now, to actually do this project, you will need 2 libraries, which is going to be either libdnet, which is specific, I guess, to Fedora, although what it's specific to may have changed, because it's kind of the same library, just under different names. Now that'll be either libdnet or libdumnet, or sometimes just called dumnet as well. The other one is libpcap, and that should be pretty consistent. You could download them with a DNF or apt, or you could download them directly from GitHub. Okay, now we can actually start on the code. So let's just write a simple main.c. Now for transparency, I have written this beforehand, so I'm going to be referencing that. Now of course we're going to get the usual library header files. Now this will be for the open syscall wrapper. This should be for the actual structures that we're going to be using to work with Pcap files. Now why do we need this one? We need this one because this will come up when we actually get to it. So network and host, so the network, kind of think of it as its own abstract environment, and the host is something physical. And essentially the network has its own byte ordering. I can't remember it's little or big Indian, but the point is that when you're sending traffic over the network, you have to convert this host sequence data. Let's say that you're using like x86 uses little Indian. If you send this data over the network and it turns out the network doesn't use little Indian, you have to convert it beforehand, and then once the network sends it to the other host, which let's say also uses x86, you then have to capture this traffic, and then you have to convert it back to the host Indianness. That's why we installed are importing the dnet library. That also applies to, I believe this is for a different reason, but we also do need this one. And then we don't have header files now, but I will include them prematurely because we will need them. Okay, So let's first write our main function. So we're going to make this kind of a simple program. All we're going to want to do is ensure that the input is at least like the file, the executable itself, and a single command line passed pcap file. So we can just do like a quick check of if argc equals 1, return -1, and then we have to actually open the file that we passed through the command line argument. So int fd equals open argv1. That's the file, the pcap path that we're going to pass, and then we just want to read it. So we're going to use this read-only flag, and then we just error check that if fd. Oh, it's a negative. I guess it's better to check if it's 0. We just return -1 as well. Now, again, as we said, there are two parts to a pcap file: the global header and then the actual packet records. So what we can do is just have two functions that we call and then return. So we can call the first one pcap global. I wouldn't even, yeah, let's just keep pcap global header.fd, and then we read the actual individual records in the file. We can pass the file descriptor there as well. You know, this would actually be pretty vulnerable to a race condition attack because we're passing an open file descriptor without locking it or anything. We would close that, and then I guess we just, for formatting's sake, and then return 0. Okay, now let me open this in tmux. Oh, okay, so go back to main.c. And also let's change the name from main.c to packet.c, so we can also create that header file, packet.h. Okay, so again, we're going to need those files we were talking about. Oops. Okay, there. So we're going to need parse pcap. I'm sorry, we're not going to need that. We're going to need read pcap global header, and that takes an integer. And just leave it like that, I guess. Oh, this is supposed to be void. Read pcap packet, and that also takes an integer file descriptor. And then we can have a third function which we'll call within the packet, or the read pcap packet function, so we can read like the actual individual properties of a TCP packet. Let's just read TCP packet, and then so essentially the way we're going to do this is we're going to actually we're going to buffer the packet bytes themselves and then process them individually, because we're going to be generally pcap files don't just contain one individual like network traffic packet. They contain like a sequence of them, so it's better to buffer them in a character buffer, then once we're done with it, just like empty it and fill it again. So we're going to use an unsidecar packet, or I guess we shouldn't list that. You know, let's just see. Then we have 2, and if the header, that looks right. Okay, well, let's just shrink this because we're not really going to be using it. Okay, go to packet.c. Now we can start to write the actual functions. Now first, because it is first, we could go ahead and read the oh, I guess because we did use a different name, let's use packet.c. Okay, now first we can start by reading the global header. Pass that. Now we're going to be using that struct that we talked about that we get when we import the pcap.h library. Now that will be struct pcap file header, which is pretty convenient, and we can just call that pcap file header. And essentially, let's just say, it probably isn't, but let's just say for example that the header is 20 bytes total. Okay, well if we didn't have this structure, we would actually have to individually read every one of those. With this, we can really just read, like we can pass a file descriptor to the open pcap file, and then use this struct that we use, to store what we're gonna read, which would be here. And then we just use the size of the struct itself, so we know how many bytes to read, which is the reason that we import this, because it's just really convenient. Now, this does move the cursor for the file descriptor as well. So we've completely skipped the global header, and now the cursor should be at the first byte of the records, and that first byte of the record should be it should be the header for the first packet captured. Now we could just do some printing of the data we get, so it's just a global header. Let's do like version major number, and now these values are unsigned. You can see here that we get access to all of the fields. Now let's just do version major. We really don't need any much more than that, because that's not the point of this video, but you can print out all the fields if you want. Alright, so that's the first thing done. Now, okay, so we are going to also have to create that packet reading.h header file. And that's just going to I'm sorry, I meant we're going to need our file info header file. That's just going to store different structures that we define, because depending on the system you're on, you kind of do have to set structures for like time v and packet header time, because it's not really the same on every system. So this is good practice when you're working with these libraries. Okay, let's do that. And then also we can just define a few macros if we need them. Struct time v. We're specifically going to do this time v declaration because when we print out the times that are used in the packet capture, there can be issues using printf and whether it's signed or unsigned. That's why we're going to explicitly set them here. Packet thdr. And this is just so we can have access to that time structure along with other values. Should make programming this easier. And then we just end if. Now there's really no reason to be working I'll just keep tmux open. Alright. Now we can now we can start to write the function to read actual individual pcap files. Sorry, just cleaning something up. that should be, what's the issue there? Oh, I should have called this packet reading. It's called file info.h. Oh, that wasn't meant copy. Yeah, let's just do this again. Or not even copy, it should be move. File info.h. There we go. That works. Okay, now we can actually start to write the function to read the individual records in the pcap file. It should be void pcap packet int fd. Now, this is going to be the structure that we declared in the file/info header file. This allows us to, this essentially does what this does. This pcap file header struct, but we're going to do this for individual records. Now, the pcap.h library does include it, but again, there is issues with the signess /word width of the time values, which is why we're going to write our own version here. And then we also need a buffer to store the individual packets to process them. It doesn't have to be that big, because these packets don't usually get that large. 65K should be fine. And then we need an unsigned value to store how many packets we've processed. And a base, like a start, it's kind of like a stopwatch. We need to set a base so we know where we started off. So like when we process a packet and it has a timestamp, we can just add it to our base to see like how many microseconds has passed since this packet was captured. So we need the base usec. And we can set our first packet to 1. Okay, now we're actually going to start to read the individual records. So we can just use the read function for that. And we're going to be reading the header first for each packet. And then size of the packet header we're going to read. HDR. Now while this is valid, reread the I guess if you don't really know this about C, even though this is a conditional, we're actually still executing this. So after this condition passes, we're actually at the start of the first, like the real packet data. Okay. Now we actually read the packet data of the TCP or whatever we're going to be reading is. We can read that into a buffer. Cap length. That's the size of the actual packet that we're reading. Now we check if first packet. Now we're actually going to check whether the packet we're reading currently is the first packet. That is because we do want to set like the base time values, like, oh, this first packet was received at this time or sent at this time. At this point, start like the quote-unquote timer. Now we can fix this, or we can set this condition to 0 such that it doesn't execute again. And then we can use the time stored in the timestamp. t.tv sec. We can do the same with the microsecond. pkthdr.tsatv.usec. Okay, any issues? Let's see this. Oh, we forgot the semicolon. Okay. Now after we set this quote-unquote timer, we can start with actually computing the time that we're going to be storing, or the time that's currently set now, presumably after this packet's been received. Now you'll notice that when it comes to working with TCP, or really any file type or network file type, the time that you work with is very important, because time's kind of the essential. You can't have a packet that was sent at like 2 seconds be received a packet that was sent late. I'm sorry. You can't have your packets essentially just kind of mishmash when they arrive. There are preventative measures when it comes to that. TCP has its own like sequence number, so it knows which packet came after what. But we're not working with that here. We're kind of essentially just like manually making sure that each packet is coming when it should come, and doing that by setting the time based on the timestamp that's in the individual like TCP header. We also do that for microseconds. Base USEC. Now, the reason we're writing this is to just essentially like quote unquote run the stopwatch so we time can progress. One, two, three, 1, 2, 3. Oh, meant to. Oh, wrong one. Now here we could just actually print that we print what packet it is. Now I'm not going to do this by hand because I did write it beforehand, so I will just copy that. Oops. You can see if this function is finished, now we just actually have to read the individual details of the TCP packet, because this just reads the record for the Pcap file format. It doesn't actually read anything for the TCP file, or I guess a network capture file. Okay, now we can actually go ahead and start to do that. Now this is kind of a long function, so for certain parts I'm just going to copy based on what I've already written. So TCP packet, 1 second char, and then again we're going to be processing each TCP packet with a buffer, so we're going to pass a pointer to that. Now a TCP packet, it really, again, if you recall the concept of encapsulation, it has first the Ethernet header, which is how like how different computers on the same network communicate, the link layer protocol, and then the network layer, which should have an IP header. That's kind of how computers communicate with each other across different networks. And TCP header, that's the for the application layer. That's how, for the transport layer, that's how it knows like what port to go to on the specific computer and what specific port. Okay, so we have to the Pcap. I believe this is the iNet or the dumbnet. It does provide us with structures to quickly read these headers. This one for header, and rather than having this like on the stack, like one way we could do it is just literally just to like have the structure on the stack. This is really memory inefficient, so it's just better to store them as pointers and then fill them out later. Or I'm sorry, because we're already passing. Okay, so what we're passing is already in is already in memory. So rather than just creating these structures again, what we can do is just have them point to the position that part of the okay, so just to like clarify, this packet buffer is storing our TCP packet, and that's already in memory. So this, Like the reason we're going to use pointers is because we can simply just point to the start of the Ethernet header in the buffer. Like let's just say that's like 20 bytes, and then we can and because we're using this struct, it knows that from the start of where the pointer points to, like 20 bytes plus, that's going to be all Ethernet stuff, so it can access individual fields of the Ethernet header without issue. That's kind of how it works here as well. So if it knows, like this IP header intuitively knows, okay, we're encapsulated inside like some kind of TCP UDP, but I know that in the entire traffic capture, I'm going to start at a specific point, and then I'm only going to read a certain amount of bytes. That's why we're not really wasting memory here. We're just going to use what we already have and just reference it different ways. Kind of a long explanation, but it's a good way to optimize your code, because I know a lot of people would probably just use like that, and then you're just kind of using up a lot of stack memory that you really shouldn't. Oh, this should have a... Okay, and that should be IP header. Oh, I'm sorry, I thought those were the, what do you call them? The actual struct names. No, we went for TCP. Nope. We can start by actually reading the, or not, I guess not reading it, we're just referencing what we already have. This will make a lot more sense when I actually write it out. So what are we setting this pointer to point to? Well, we're setting it to point to the start of where the Ethernet header should be in this encapsulated TCP packet. See, that's the key here. We're typecasting it. When we typecast it, we're essentially saying like, okay, because really, if we didn't use this typecast, all three of these would just point to the beginning. Because we typecast it, it's gonna like intuitively know, oh, because we're using this specific typecast, I know that the Ethernet header will always start at like this specific byte offset, and then it's going to read these many bytes as part of its header. Do that, and then if we're just going to print out, now we have access to the Ethernet header. Rather than typing all that, I'm just going to copy from what I have. Okay, and you know, the same kind of applies for every other header in this captured packet. I'm not going to write all that because it is really just all the same. For networking, for the network and TCP packets, I will point two things out. Let me just copy them. Okay. So again, we're doing the same thing here, but notice that we're going to use the length of the Ethernet header to offset where we're going to point to. This just tells it, okay, from the position we are at now, read this many, consider this many bytes as part of your memory. And then, like, let's just say that the Ethernet header starts at offset 0, and let's just say for argument's sake that this is 50. By doing this, we're going to go from 0 to 50, which is where the IP header starts, and then we're going to only read the amount of bytes that the IP header is made up of. That's kind of the efficient way of doing things. Okay, and this is again what I was talking about when it comes to host and network byte ordering. Now here, the Pcap stores things in network ordering. So when we read the individual bytes from the IP header, we have to convert those to our host sequence, our host ordering, which I believe for x86-64 is Little Endian. And it's really all it's doing. It's just kind of reversing the byte order, and then we can properly print out the real value with an unsigned string format. That kind of applies here as well. Oh no, I'm sorry, that doesn't apply here. The source and destination IP addresses are stored as unsigned integers, Now I do know that there are certain functions for converting your IP from either decimal or a dot notation, a decimal value, or hex. I didn't use that in this case, but there are those functions in case you need them. Those are strictly mostly for like readability though. Now here we just read the individual values in dot. There was a function to do this, but when I did write this program a few months ago, I didn't know of the existence. I recently read about them in the Linux programming interface book. But in that case, you would want to use that function. I can't remember the name of it, but the function does exist. Here, this is kind of doing it manually, where we convert it to an unsigned 8 integer. Sorry, an unsigned integer, and then just read the individual values in dotted notation and format it. Now this is just a way to calculate the IP header size, so that we can then use it again, similarly what we did here, to offset the address that we're gonna set the TCP header to point to, and then again this typecast is just to say from this position that we're pointing to, this many bytes belong to us. Okay, and then this is kind of what we're doing here. And then the TCP is a lot more simple. Again, we're doing the network to host conversion. It is worth noting that these are shorts and these are long values. There are different words, I guess, it's the same function, but it's for different word sizes. So the sequence and ACK numbers are longs and the ports are shorts, which I guess makes sense. Ports only go to like 65,000, so yeah. Alright, so that should be really it. Alright, let's look for any errors. I believe I called it something else. Global header, I forgot. Alright, for any errors. Okay, now we're good to compile this. Yes, I still like to use GCC. Just call it Pcap Parse. And then we do need some flags because we're going to be, this is something you can do in the makefile or I guess here in the command line when you're compiling it. We do need to include the libpcap flag as well as the libdumnet or dnet flag as well. Now let's compile that, pcap parse, and then we can pass our sample pcap file. Alright, so it did just capture a single 2 packets. I believe, yeah, this is a bit of a shorter one. Oh, I'm sorry. I recall now that this is actually an outdated version. What we want to do is get the TCP charge, and I guess we'll just call it that. And charge into sample.pcap, and then we can actually do the test that we're supposed to run. Here we can see that there are actually 21 packets, and let's just pick a random one. Here's that time we were talking about. We're accurately computing it in microseconds, and then the sequence and ACK numbers, you can see that they are always greater than the last one. You can see that the source and destination ports are as they should be, because the sender receiver. And then the captured packet length, the Ethernet at source and destination, that also should be flipped between each packet unless there are retransmissions or more than one packet sent. And then we accurately have the number of packets sent. Right, and then I guess we could also print out more data if we wanted to about the pcap file itself. And it looks here, no more ACKs. What actually happens here? Looks like this is a retransmission because there is no ACK. Okay, that's cool. Well, I hope this was useful. I know it is kind of a messy concept because, even I have trouble understanding it a little bit because Linux has so many You have your different domains, you have different sockets, and then when you actually have to like get into working with network file types that do actual networking, you have to worry about like net to host or host to net. It can get a little bit complex, but overall, when it comes to writing a simple program like this, you just have to follow the specs for Pcap, and then whatever protocol you're going to be focusing on. Here we did Ethernet, network/IP, and TCP. But if you're going to be handling other ones, I believe Wi-Fi. I forgot the name of the one for Wi-Fi. I think it's like 802.11. If you're going to be worrying about that, you have to add like a conditional saying like if this Ethernet packet says that it's Wi-Fi or 802.11 or Ethernet, then handle it as you should. Alright, well I hope this was useful to you. So have a nice day. Thank you.